All right, so let's start. Let's start today's lecture. So today you are going to learn about refraction and then lens. Okay. So this simulation you already see in last lecture, where we try to understand the reflection, the concept of reflection. Okay. So let's see what we see. Okay. So you see here we have a laser light. Okay, laser light, and then we have a beam. Okay, or I mean in our language of geometric optics it is a ray. So this is the incident ray. It strike on the surface, and you see the some part is reflecting, and we already know the law of reflection. Okay, so if you forget, here is the law. So the incident angle, or the angle of incidence, is equal to the angle of reflection. So this is the angle of reflection. Okay, so this part you already learned. The next thing is the rest of the uh, rest of the ray is transmitted through the medium. Okay, so you see that this is transmitted through the second medium. So here we have air. So you see air, and then this is water, for example. So this is a transparent medium. So if the medium is transparent, then part of the light could transmit it through the medium. So here this is okay. So this phenomenon we call refraction. Okay, so this part is this ray is part of reflection. This ray is part of refraction. Okay, now we are going to learn more about this. Okay, now to understand uh, refraction, we need to understand some properties of the transparent material, and we call it index of refraction. So here you see that index of refraction for air is 1, and the index of refraction for water is 1.33. For example, if I use glass, so you see that index of refraction for glass is 1.50. Okay, so let's learn about that, and then learn more about refraction. Okay, so let me go to the study guide. Okay, so let's learn more about index of refraction. So the index of refraction, we use this symbol small n. Okay, small n is the index of refraction, and this is the ratio of the speed of light in a vacuum. So c is the speed of light in vacuum, and v is the speed of light of a particular medium for which um, we are I mean, uh, for a particular medium, for example, glass or water. Okay, so if I want to know what is the refractive index of refraction, I mean index of refraction, or the refractive index for water, then this is the ratio of speed of light in vacuum, that is a constant, and the speed of light in water. Okay, so this is the speed of light in vacuum, and this is the speed of light of water. Okay, so if I want to know what is the index of refraction for water. Okay, now c is the speed of light in vacuum. That's a constant number. Okay, and the value of c, the speed of light in vacuum, is 3 times 10 to the power 8 meter per second. Okay, 300 million meter per second. Okay, and it is a vacuum. Okay, so remember this is a vacuum. Okay, and in air it's slightly less than that. So in air, light travels with almost this speed. Okay, it's little less than that. Okay, I don't have the number here, but it's almost the same. Okay, so so for simplicity, in any calculation, if you want to know, if you need to use um, the speed of light in air, we are going to use this number. Okay, although it is a speed of light in vacuum, we are going to use this also for air. Okay, and remember that air is not vacuum. Okay, now um, now here I give a table, and this table shows the index of refraction for different material. For example, vacuum, it should be 1, because c divided by c is 1. In air, it's slightly less than slightly greater than 1. Okay, why it is slightly greater than 1? Because v is slightly less than c. Okay, so that's why it is slightly greater than n is slightly greater than 1. Okay, for example, in water, v is this. Okay, 3/4 of the speed of light in vacuum. So if I use this v here in this equation, you can show that the refractive index of water is 1.33. Okay, and so on. Okay, all right, so it is a property, I mean, the index of refraction is a property of the material, basically property of transparent material. Okay, and we need this property to understand the law of refraction. Okay, so the next thing we are going to learn is something called law of refraction or Snell's law. Okay, all right. Okay, so before I move to that, n is always the refractive index or index of refraction is always greater than 1. Why? Because v is always less than c. Okay, the speed of light in any transparent material is less than the speed of light in vacuum. So that's why the refractive index or the index of refraction is always higher than 1. Okay, and that means light travels more slowly in matter than in vacuum. Okay, now what is the uh, law of reflection? So first let's learn about that and then come back to here. Okay, so the law of refraction we also called Snell's law. Okay, so here you see that Snell's law. Okay, this is Snell's law. Snell's law tells us this: n1 times sine theta 1 equal to n2 sine theta 2. Now, what is n1, what is theta 1, what is n2, and what is theta 2? Okay, to understand these, let's go to the simulation again. Okay, so here you see that light is going from air to water. Here in this case it is glass. Okay, so the refractive index of air is n1 and refractive index of glass is n2. Okay, so if I mean n1 means where we have the ray of incidence. So here you see the ray of incidence is in air. Okay, so that's why n1 is the refractive index of air, and n2 is where we have this ray, I mean the refracted ray. Okay, so because it is in water, so n2 is the refractive index of water or glass. Oh, sorry, for example, here it is glass. Okay, so the first medium is air, second medium is glass. So n1 should be for the first medium and n2 should be for the second medium. Okay, and what is theta 1? Theta 1 is the angle of incidence, so this is theta 1. Okay, and what is theta 2? This is theta 2. Okay, so so this is theta 1, this is theta 2, and this is, as you already know, this is called angle of incidence, and this is called now angle of refraction. And the law tells us n1 sine theta 1 equal to n2 sine theta 2. Okay, so remember that n1 times sine theta 1 equal to n2 times sine theta 2. Okay, so this is the Snell's law or angle of refraction. Sorry, a law of refraction. Okay, now here we have to understand two things. Okay, now here let's come back to here, and here you see that light can incidence from air to water, for example here, or light can go from water to air. Okay, so as you know, the index of refraction for air is 1 or close to 1, and water is 1.33. Okay, so here light is going from low index of refraction to high index of refraction. Okay, and here you see that light is going from high index of refraction to low index of refraction. Okay, Now, so here you see when light is going from low to high, then you see that refracted ray is banded towards the normal line. So you see that it should be, if it is water, the ray should be, okay, so let me go here. Okay, so here it's basically the same thing. Okay, so light is going from air to water. Okay, so if light goes from air to water, that means low index of refraction to high index of refraction, then this refracted ray bends toward this normal line. Okay, so you see that okay, so what it means, so you see that, so this is the, if both are water, if both medium are air, so it should be, you see that it should follow this line. But because this is water, okay, you see that it bends towards the normal. So the rule is when light goes from low index of refraction to high index of refraction, it bends towards the normal line. Okay, now if opposite happen, that means if light goes from water to air, okay, so you see that light bends away from the normal. Okay, so if both are water, you will see that this is the line. If light goes from water to air, that means high index of refraction to low index of refraction, then it bends away from, so you see that it bends away from the normal line. So this is the rule. Okay, so here you see that there's two picture. In one picture you see that light is going from low index of refraction to high index of refraction. In this case, refracted ray is bended toward the normal line, and in this case when light is going from water, so here light is going from here to here, so water to air. So here you see that refracted ray, so this is the refracted ray. Refracted ray is bent away from the normal. Okay, so this is the rule, remember that. Okay, all right. Now many of you are familiar with this kind of pictures, I believe. Okay, so you see that it looks like broken. So when you put a spoon in water, half filled water, it looks like the spoon is broken. Okay, and this is basically the basically due to the refraction. Okay, this is due to the refraction illusion. Okay, so here this is interesting, right? You see that it looks like the body is displaced from the head. Okay, and again this is the refraction illusion, and the same thing here. Okay, you see that bodies or heads looks like displaced from the bodies. Okay, again this is the this is the this is due to the refraction. All right. All right, the next thing we are going to learn something called total internal reflection. Okay, although it is although the name is total internal reflection, it is basically a refraction phenomena. Okay, so that's why we are talking total internal reflection here instead of talking it in the reflection section. Okay, so what is total internal reflection? Okay, so to understand this, we need to understand that it happens, the total internal reflection only happen when light is going from high index of refraction to low index of refraction. Okay, so when light goes from water to air, you can see the total internal reflection. Okay, not from air to water. Okay, so remember that the first condition to see the total internal reflection is light should go from high index of refraction to low index of refraction. Okay, so water has high index of refraction than air, so we can see total internal reflection. Okay, so let's go to the simulation again. So here light is going from water to air. Okay, so we can see the index, I mean the total internal reflection. Okay, so what is the total internal reflection? So here you see that if the angle is, let's say, now the incident angle is about so this is 60, is about 50. Okay, so let's say, let me start from 30. Okay, so now it is 30. You see it is 30 and it should not be 30. I mean, this is angle of incidence, angle of reflection should be 30. Okay, actually, yeah, so you see that this is 30, this is also 30, but it is not 30 and it should not be, because the law is n1 sine theta 1 equal to n2 sine theta 2. So this is theta 1, this is theta 2. So in this case it should not be 30. Okay, so 30, and here you see this is it looks like 35. Yeah, so it follows this rule. If I write down here, it will be n1 sine theta 1 equal to n2 sine theta 2. Okay, now so that's why if it is 30, it should not be 30, because it follows this rule, not just theta 1 equal to theta 2. All right, so the thing here I want to show you here is as light is going from water to air, so the refracted ray, so this is the refracted ray, it should be away from the normal. So it is away from the normal, right? So if both are water, the ray should go follow this line, but as light is going from water to air, so you see that it is going away from the normal line. Okay, now if I increase the angle of incidence, so you see that angle of refraction is also increasing. Okay, and at some point it becomes 90 degree, right? It's very difficult to show when it is 90 degree. We have to bring it very slowly. I mean, we have to move it very slowly. Okay, so you see at some point it will be 90 degree. I mean, I cannot show here it is exactly 90 degree, but yeah, very close to 90 degree. Okay, so so that means as you are increasing the angle of incidence, at some point the refracted ray is parallel to the surface, parallel to the surface between the two medium, right? So that means at some point the angle of refraction or theta 2 is 90 degree. Okay, so for example, this is, if this is 90 degree, so theta 2 is 90 degree, right? So if theta 2 is 90 degree and sine 90 degree is 1, okay, then we can rewrite the equation, this equation, as, okay, so now this part is 90 degree and sine 90 degree is 1. So this is basically this n1 sine theta 1 equal to n2. Very simple, right? So it has some special name. When the angle and the refracted angle is 90 degree, I mean when theta 2 is 90 degree, the incident angle theta 1 is called critical angle. Okay, so we use a symbol theta c for critical angle. So this is the critical angle. Okay, so for example, when light is going from water to air, this angle is the critical angle. It's about 30, 40, 50 degree. Okay, so 50 degree, I mean, we can calculate exactly what the value of critical angle for this case. Okay, so critical angle is the angle when I mean when the light incidence at that angle, the refracted angle is 90°, or the ray of refraction is parallel to the surface. Okay, so remember that the angle of the critical angle, when the light incidence at critical angle, the angle of refraction is 90°. That means this refracted ray is parallel to the surface. Okay, now if we keep increasing the incident angle, okay, it will be no longer in the second medium, it will be in the first medium. All the ray will be in the first medium. So if you see here, if I keep increasing, so you see that there is nothing here in the second medium, all the ray in the first medium. Okay, so because there is no refracted ray, all the rays are now in the first medium. Okay, we call this phenomena as total internal reflection. Okay, so all the rays are reflected rays. Okay, I mean, incident ray, there is no refraction, there is only reflection. Okay, so when light goes from high index of refraction to low index of refraction, then if the light is incident at an angle higher than the critical angle, there will be no refraction, there will be no refraction, there will be only reflection, and that phenomena we call total internal reflection. Okay, all right. All right. So here I show that if we start from uh, the Snell's law, you see that critical angle can be written as the ratio of n2. N2 means the second medium. Second medium means where we have the refraction, and n1 is where we have the incident ray. Okay, so n2 is the index of refraction, where we have the refracted ray, and n1 is the index of refraction, where we have the incident ray. Okay, so this is the ratio. The sign of critical angle is ratio between n2 minus n1. I'm sorry, n2 ratio of n2 and n1. Okay, so you have to understand what is n2, what is n1. Okay, n2 is the second medium where we have the refraction, and n1 is from where the light is striking a surface. Okay, all right. Now the total internal reflection has many application. Okay, in for example, fiber optics. In fiber optics, um, um, I mean, this phenomena is used. Okay, and you probably know that fiber optics is used in many medical instruments, for example endoscope, in communication, for example transferring data from one place to another place. Okay, so these are the two important application of total internal reflection. Also, the sparkles in diamonds are due to the total internal reflection, and in also in binocular, total internal reflection is used. Okay, so here you see that light is so this is a part of a fiber optics. So here you see light is incident here in this optics. So the surface here is between the fiber optics and air. Okay, so light is going from basically fiber optics to air. The index of refraction for the fiber optics is of course higher than air, so we can see the total internal reflection. Okay, so if the light is incident at an angle higher than the critical angle, there will be no refraction. So you see that there is no refraction here. I mean, there is no light passing from fiber optics to air. All the ray is reflected ray. Okay, so and this phenomenon we call the total internal reflection. So here you see, so based on that, the endoscope, so endoscope is basically I mean, here this is a fiber optics. Okay, so we use this to see the internal organ. Okay, so if there is some problem in the internal organ, um, by connecting this with the camera, we can see whether there is any problem inside. Okay, and also this is used in transferring data, I mean internet data, for example. All right, so that's about total internal reflection. The next thing we are going to learn is thin lenses. Okay, all right, so these are the some example of lenses, thin lenses. So lens could be okay. So here we have two refracting surface. So you see that it is made of two refracting surface. So here is one surface, there is another surface. In all lenses we have two refractive surfaces. Okay, now we are basically interested on double convex lens and double concave lens. Okay, so you see that the surface where the light strikes are convex here. Okay, and here both are concave. Okay, so we already know what is concave and what is convex, right? Convex mirror, we already learned about convex mirror and concave mirror. So similar to that we have these. Okay, so we are not going to learn these. Okay, so here we have a convex surface and a straight surface, and here we have a concave surface and a straight. So we are not interested on that. We are only interested on double convex and double concave. Okay, now remember that in mirror, uh, concave lens, the concave mirror was for converging the parallel rays. Here it is opposite. Here the convex lens is used for converging, okay, converging the parallel rays. Okay, so it's opposite. Okay, you will see. All right, so double convex lens we are going to use to understand the converging the parallel rays, and double concave lens we are going to use to um, diverge the parallel rays. Okay, now here you see this is, we have two spherical part. So here we have one part, here we have one part. So for this one we have also one and one. Okay, so that's why, because we have two spherical part, both double convex lens and double concave lens has two focus, two focal point. Okay, and two focal length. So if it is a double convex lens or a double concave lens, it doesn't matter from where, from which side the light is passing. Okay, so it is always be the same, no matter whether light is going from this direction or from this direction, or this direction. Okay, all right, so here you see that for a um, double convex lens, light is going striking in this surface. Okay, and then um, they meet at this point, they converge at this point. And here you see that interesting thing, here you see that the light is passing through this lens. Okay, that means refraction is happening here. Okay, so here for convex lens, you see the light parallel rays are meeting at focal point. Okay, so here is another one. If they are all parallel but not parallel to the principal axis, they will not meet exactly at the focal point, but in the plane of the focal point. So here you see. Okay, on the other hand, for double concave lens, you see that it is striking here, passing here, and then if you extend the refracted rays, so these are the refracted rays, so if you extend the refracted rays, they meet at the focal point. Okay, so it has two focal point, one is on this side, another is in this side. So if light is passing, light is striking when the parallel lights are coming from this side. Okay, they look like they are diverges they diverge from this point, this focal point. Okay, now in mirror, what you see that images are produced by reflection, and in lens images are produced by refraction. Okay, so that's the difference between the mirror and the lens. And also you see that here concave I mean convex mirror are converging convex mirror are converging, sorry, convex lens is converging lens, and concave lens is diverging lens, which is opposite to the mirror. Okay, all right. So yeah, another difference is in lens, the images are produced. So images we are going to learn in the next slide are produced by refraction. In mirror, images are produced by reflection. Okay, all right. um, so how the image form is very similar to what you see in the mirror. So when parallel rays strike um, the lens, it refracts and it meets the focal point on the other side. Okay, so here you see it meets on the other side. Okay, now so this you already see, this is one. And if the incoming ray or the ray goes through the focal point, so you see here this is going through the focal point and strikes the lens, so after refraction it will be parallel to the principal axis. So this is the principal axis. Okay, so after refraction you see that it is parallel to the principal axis. Okay, so if before refraction, if it is parallel, then after refraction it will be going through the focal point on the other side. Okay, if it is going through the focal point after refraction, it will be parallel to the principal axis. Okay, this you already see in case of mirror, right? Now this one is third one is different. Okay, so if the ray is passing through the center of the lens, it will not change the direction. So here you see that it is passing through the center. So this is the center and there is no change in the direction. Okay, so here you see that. Okay, so when the refracted rays, all the refracted rays meets, okay, we see the image. So here you see that these three rays, refracted rays, are meeting at this point. So this is the image. Okay, now here you see the image is on the other side of the lens. Okay, so image is the other side of the lens. Okay, and this type of image we call the real image. And you see that this is inverted. Real image is always inverted. So here you see that inverted image. And in case of if we use double concave lens, you see that image is here. So if image and object are both in the same side, okay, we call this kind of image virtual image. Okay, so it is different from mirror. Okay, so mirror image concepts are different than lenses image. Okay, so you have to remember these. Okay, all right, so we'll discuss more about that. Okay, so similar to them, now let's talk about the equation. The good thing is the lens equation is and mirror equation is exactly the same. So here 1 over di is the image distance, 1 over do is the object distance, and 1 over f is the focal length. Okay, and also the magnification is very similar or same actually. So m is the image ratio of image height and object height, or it could be the negative of image distance to object distance. Okay, now here we are going to understand the sign convention. Okay, sign convention is very important because this equation and this equation I will be giving Okay, so you don't need to remember that. You have to understand how we use the sign. Okay, all right. So before we do that, let's first see this simulation. Okay, so this is converging lens or double convex lens. Okay, so here you see that we can have both image. So here this is a real image is inverted, or we can also have um, the virtual image. Okay, so this is the virtual image is upright. So for this lens, double convex lens, we could have both images. On the other hand, concave lens, we have only one type of image. This is the virtual image is upright. Okay, so it is you also see um, similar thing um, in mirror, right? All right, so if you see the equation, okay, so here you see that the focal length for this kind of lens or the diverging lens or the concave lens is negative. Okay, so remember that for diverging lens or concave lens we use negative focal length. So f is negative for this lens or concave lens. Okay, and object distance is always positive because we can control it. Okay, I mean most of the case it is positive. Okay, there are some complicated problem which we are not going to do, but for our case most of the time or almost all the time the image I mean object distance is positive. So here you see this positive and this is the image distance. So image distance is negative if it is in the same side. Okay, so here you see that it is in the same side. I mean what I mean is if image and object are in the same side of a lens, the image distance is negative. Okay, so remember that. And similar to the mirror, if it is upright we use the positive sign for the image height. Okay, if it is inverted we use negative sign for the image height. Okay, now for convex lens, so object distance is always positive, the focal length is also positive, and if the image is on the other side, okay, you see that it is positive. Okay, so the image distance is positive and image height will be negative because it is inverted. Okay, now if we have this, okay, for a virtual image, now you see that image and object both are in the same side of the lens. Now you see that object distance is positive, focal length is positive, image distance is negative. Image distance is negative because both object and image are in the same side. Okay, all right, so that's about the sign convention. I already summarized here, so please go through it. And yeah, so this is important. So for diverging lens or the concave lens, I mean double concave lens, we can only see virtual image. But for other type, I mean when it is both I mean double convex lens, okay, or converging lens, we can see both types of images. Okay, real and virtual images. And those who use glass, remember that farsightedness can be corrected using converging lens. Okay, while the nearsightedness can be corrected using the diverging lens. Okay, so what is farsightedness? Farsightedness means those person who only see better the far I mean the distance object. Okay, and nearsightedness means the person who just see clear the near object. Okay, for example, um, uh, I have this problem, nearsightedness. Okay, so I can only see better the near object. Okay, I cannot see the object that is far. Okay, all right. The last thing we are going to learn is lens combination. Okay, so lens combination means, I mean, when we have more than one lens in action. Okay, so when we have more than one lens in action, we have to analyze each lens separately. Okay, so for example, we are going to do at least one problem, one simple problem. For example, this problem. Okay, so if we have more than one lens in action in some problem, so we have to analyze this lens first and then the second lens first, second lens then. Okay, then if we want to know what is the total magnification, okay, so if we have an object, so it will be it will create some image somewhere. Okay, and then this will also create some image. So if I want to know what is the total magnification, I mean the combined magnification, then we have to just multiply. For example, let's say we get a magnification M1 for this lens and M2 from this lens. So if I want to know what is the final magnification, so here it asks to the magnification, the final magnification. So the final magnification will be M1 times M2. So we will be doing this problem in the next class. Okay, so that's only the difference. Okay, you analyze this lens first and then this lens, and then finally if you want to know what is the final image magnification, you have to do something like this. Okay, and another thing is, for example, let's say we have the object here. Okay, let's say you get image of this object somewhere here. Okay, now this image is now the object for this lens. Okay, so that's the difference. Okay, so by assuming that this is the object of this lens, we have to find the image from this image formed by this lens. Okay, and then we have to calculate separately the magnification for this lens, and then combine them by multiplying them. Basically, that's it. Okay, so we will be doing the problem in the next class. All right, so that's basically all about the concept. So please go through this. Okay, in the next class we will be solving this problem. So we have to solve problem 5, 6, 7, 8, and 9. Okay, I'm not so this number 10 is not for you. It's a little bit complicated problem. So this 5, 6, 7, 8, and 9, this 5 problem we'll be doing in the next class. And if you have time, we are going to start a new chapter. All right, so that's it for today. And if you have question, please email me.